So in this video, I'm going to show you how to do some more advanced statistical models in R. So let's start with what we've done before in these previous videos where we set our working directory. So anything that I type into a script here, I can highlight and click run, or I can press Control Enter on my keyboard and it'll launch and run. And you can see that it's setting the current working directory. I've got a script open here that I've called walkthrough2 that I'll upload along with this video, and you can see that I've got a couple of comments. I also have my R markdown that's a little bit more detailed about what we'll be doing in today's walkthrough. So today we're going to be working with some data that's the same set of calculations in two different programming languages, which makes it really nice for comparing the system runtime, or sys runtime, of the amount of time it took for each programming language to do the same set of calculations on the same input file. Generated a data set that we'll now read in, and we'll analyze that in R as a way of looking at statistical differences between the sys runtime for those programming languages. So let's start by, what I've done is I've taken that output from the Microsoft form, and I've saved it as a CSV and done some minor cleanup to it. And so now we're going to read it as a CSV into an object called PVA. So let's just do a quick read CSV, and let's look at that over here. So here we have when it was started, when it was completed, your email, so this is the students in the class, your name, and you included things like your operating system, your programming language, your sys runtime, and your input VCF file size. Remember, you used head to get a smaller version of it versus the full file. So we have two different file sizes. We actually have three different languages because your TA included some Python data here. And then a couple of you put in data sys runtimes of things like 30 minutes. So we went ahead and converted those to NAs, and then some of you put did not finish, so we converted those to NAs. So there's this sort of consistent NA among some of the data sets. Okay, so we have 37 observations across this data set. Because we have NAs, if we do a quick summary of the data, this is going to give us a summary of each of the variables. So each of those columns, it's going to tell us something about them. And what you'll notice here is that our sys runtime has been entered as a character in this data set. And we know that we want it to be treated numerically. What's preventing it from being treated numerically? It's got character data in the column. But what we want to do is we want to tell R that when you're reading in data like this, this means NA. So what we can do is we can add in this option within read.csv, and this is an option within a lot of read.table, etc. And this just says NA strings, and then we're defining in our data what NA strings are. So you could have in your data put a period if it was missing, you could have put a dash if it's missing, whatever you wanted to do as long as it was consistent. And in this case, we just put NA. So you actually have to tell R, when I say NA, I mean missing data. And that's what NA strings definition means. Now when we read in this data, and we do summary of PVA, you'll see that we have sys runtime in our summary as a numerical data that ranges from 0 to 426, and we have 6 NAs. And if we look at this tab over here, you can see now these have been actually formally converted to NAs because R recognized that those NAs in our input file are NA strings, and it converted them properly. Okay. So now what we might want to do is something like plot X versus Y. So we're interested in the programming language, so whether it was Perl, Python, or awk, and the sys runtime. So let's try and plot those against each other. We get a pretty big error here. So let's again look back at this summary output. So we've got our sys runtime, and it is correctly numerical. But if we look at our programming language, it's also character data instead of factor data, where it has 3 different levels. So another thing that we can add to our read.csv is this string here, strings as factors. And what this is going to do is we're going to set it equal to true. And let's run that summary command one more time. And now you can see that for programming language, we have 3 different factors. This also worked for the different student names, email addresses, and it's basically turned everything else into factorial data instead of character data. Here you can see that we have all these different operating systems. So the majority of our data comes from Ubuntu, the Alabama supercomputer, iOS, Mac OS, iOS. So this is one of those things where looking at this, you could easily go back to your original data file and clean it up. I would assume that iOS and Mac OS are the same, and iOS with any level of capitalization is the same. So as long as you come up with a consistent naming convention, then that would group all of those into the same thing. Okay, we're not going to do that for the purposes of today's demo because we're just interested in sys runtime and programming language, and those are fine. Okay, so now that we've properly read in our strings as factors, let's try plotting that again. Okay, so now what we've done is we've created a box plot where on the x-axis we have the 3 different programming languages, and on the y-axis we have the sys runtime. Now, one of the things that you'll notice is we have this one huge outlier for our awk data that's way up here. So let's go ahead and look at the distribution of that sys runtime. And here you can see that the majority of our data is under 100, and we have one outlier that's way up at 400. So let's go ahead and say subset that's less than 100, and then let's plot it again. Okay, now we can see that it goes from 1 to 5, even though we subsetted it at 100. Okay, let's try that plot one more time, and we can see something a little different. Now here, remember, we did it for 100, and our data ranged from 0 to 5. However, you can see that the majority of our data points are actually below 1. And in fact, we only have 3 data points in the Perl output that are really long. And it could be that those were maybe not as computationally efficient as they could have been, and they're not really telling us what we want to know about whether Perl or awk or Python is faster. So let's go ahead and do a cutoff of 1 and look at our distribution again. So now we see something that's a little bit more of a continuous distribution of data among all of our sys runtimes. And if we do one more plot, we can see that now we can start to see, breaks of awk, Perl, and Python. We still have a decent number of data, or data points for each of the 3 different programming languages, and we have our sys runtime in seconds here. So there's a nice distribution. It's actually all below 0.25. So these are very quick and rapid calculations. The other thing that we might want to look at, so this is a graphical way of looking at the data. We've talked about looking at the data using histogram, range, etc. When we have categorical data like this, one of the things that we might be interested in is looking at the specific means of each of our different programming languages. So one thing that we can do is use this syntax here, where we say, in this subsetted data PBA2, I want to take only data points where the programming language equals Perl. And then what I want to do is get all of the runtimes for those data points only, and then take the mean of those. And then I can copy and paste that and change Perl for awk, and then awk for Python. So let's run this code and compare the means of these 3 different data points. Okay, so what you can see is that the Perl mean is the smallest at 0.04, and then we have the awk mean, which is 0.06, and then finally the Python mean, which is 0.08. So it looks like Perl's the fastest and Python's the slowest. And that's really what this box plot is showing us, right? Perl has a mean down here and Python has a mean down here. Are these statistically different? We'd have to run a more complicated statistical model than just comparing means. But first, let's think about what our data look like. So remember that we also had two different file sizes, the full file size and the partial size. This is probably going to have an impact on our sys runtime. So let's go ahead and subset our data to see if there's differences in the sys runtime based on whether it was the full data set or the partial data set. So let's first subset just for the full one. So we're going to do the subset the same way we did for that cutting out of the outliers of sys runtime. So we're going to use the function subset, and we're going to say we want the input VCF file size to be equal to full. And then we're going to store that in a new object called full. So let's run this. And you can see our object appears over here. We have 15 of these 27 data points are full. And if we plot those against each other, we can see largely the same trend. So the smallest mean is Perl, then awk, and then Python. We can do the same thing for small. So basically just saying the input VCF file size is equal to partial. And then we're going to store that in an object called small. And then that's going to pop up over here. So we have 15 observations that are full and 12 that are small. So a nice, good, even distribution of that data. And if we plot that, we can see, okay, Python still seems to be the slowest in that it has the longest sys runtime. But in this one, awk and Perl seem pretty head-to-head. For the small file size. So maybe there's some advantage to Perl at the large file size, but for smaller file size, awk and Perl are pretty toe-to-toe. So this is looking, again, at it graphically where you're kind of like, I kind of see where the mean is. Let's look at the actual numbers by pulling out those means again for the full and then for the small, okay? So here you can see down here on our console that for the full, we have 0.06, so the smallest number is Perl, 0.09 for awk, and then Python is a whopping 0.138. Similarly, for the small, we can see that Python is 0.037, but awk and Perl are pretty close to each other, both being 0.016 and 0.019. But again, are these statistically different? So in order to do this, what we're going to do is we're going to fit a analysis of variance model. So this is a function that's built into R called AOV. And what we're going to do is we're going to say, we're going to use this tilde symbol to say, this is our response variable, sys runtime, and this is our manipulated variable, the programming language. So we're setting this up just like a statistical model. Does the programming language predict the runtime? We can do that for both the full, and we can store the output of that statistical model into a variable called model. And since it's the full model, we can put an underscore full. And similarly, we can do the exact same thing for small. So we would call it model small. We would use that small subset, and we're going to still do sys runtime on tilde programming language. So let's run these two statistical models. And what you'll immediately see is we didn't really get any output, right? We got these objects over here. These are list objects. They've got a lot of stuff in them. Not really easy to interpret. So when you do a statistical model and you store it in an object like this, one of the easiest ways to understand the output of that model is to get a summary of it. So that same summary command that we've been using for summarizing data sets can also be used for summarizing statistical models and give us something that's kind of similar to an ANOVA table. So in this case, it would be an analysis of variance table. So let's highlight this and we'll get a summary table for both the full model and the small model. And what you can see, this is very similar to a common ANOVA table that you would get where we have the programming language is our predictor variable. Our degrees of freedom is 1 minus the number of levels that we have. So we have 3 different programming languages, so that's 2 degrees of freedom. We have sum of squares, mean squares, and some sort of F value. And then over here, we have a probability. And this is the probability that the difference in the programming languages predicts that difference in the runtime that we're seeing. And in this case, you can see that this is much bigger than 0.05, which is traditionally used as a cutoff for p-values. And this shows us that there's really no statistical difference between these 3 different programming languages for sys runtime for this calculation and on this data set. So even though we can do a box plot like this and it makes it look like, Perl's the winner and Python is not, statistically there's really no difference between these runtimes, suggesting that, you shouldn't do anything rash in terms of changing what language you prefer following this course based on this data set. Now, if you want to, you still have in the data set, if you recall, when we did summary PVA, you still have this operating system. So another thing that you might want to do, and we'll provide this data along with this video, is download the data and clean it up for the Mac OS and iOS, and then run it through this exact same code, but instead of looking at sys runtime, instead of looking at programming language, look at operating system and see if that is strongly predictive of the sys runtime, okay? And then finally, the other thing that you might want to do is look at both of these variables. You might be interested in, the interaction between the operating system and the programming language. Now, I would say with only 37 observations and 6 of those being NAs, that we don't really have the statistical power to look at any type of more complex statistical interactions in this data set. So in order to look at something a little bit more complicated, like multiple factors predicting a variable, we're going to return to a different data set that we used in an earlier video. So we're going to use that bodyfat.csv data set that we used at the end of an earlier video. We'll read that in. And one of the things that I asked you to do in that earlier video was go ahead and run that core test between the different predictor variables and see if it correlated with body fat. So if we look at this data, so we just read it in as an object called fat, you can see it has 252 observations, so and 18 variables. So it's a lot more statistical power for looking at combinations of factors. So we have our body fat, and then we have all these predictor variables. And so, like I said, you were tasked with saying, how is density correlated with body fat? Is age correlated with body fat? Is weight correlated with body fat? And so on and so forth, individually. Now, the problem with these individual tests is that, some of them can be correlated between each other. And so a good statistical test would say, okay, I have all these different variables, and I want to see which one best predicts my response variable. And in order to do that, you're going to want to do a generalized linear model. So what we're going to do is first, let's go ahead and explore that data. So here's the summary. One of the nice things about exploring your data is it also tells you if you've read it incorrectly, right? So remember when we read in that Perl versus awk data versus Python data, we had some stuff that was read in as character data. Here what you can see when we do this summary is that all of this is treated as numerical except for this last column X. So let's look at that data set. Let's inspect this X column. And I'm not really sure what happened there, but the whole column is X. So we're just going to ignore, the whole column is in A. We're just going to ignore that column and not use it. But all the other ones are read in properly as numerical, so we're good to go. The other thing that we can look at is maybe one of the variables like weight. What is the range of values? So the range of values here is anywhere from 118, I'm assuming this is in pounds, to 363 pounds. Similarly, we can look at a range of body fat, which ranges from 0 to 45. Now, if we wanted to do this to look at, how many variables are in here, just looking at this and going back and forth and picking all of these out is kind of annoying. So in R, we have this nice function called call names. And what this is going to do, I gotta let the whole line run. Call names is a built-in variable that's going to take this object fat, and it's just going to return what are all the column names. And this is a nice way to start to build our generalized linear model. So we'll do GLM, okay, and then we're going to need to do the formula, and see how when I write the object, this little thing pops up that tells me, we're going to store it in an object again. So let's call that fit equals GLM. Our response variable in this case is going to be body fat. And let me just double check that I've got that. Yep. And then what we're going to do is we're going to go through and do these other variables. Okay, and then finally we're going to say data equals, and we're going to point to fat. This is a nice thing where we don't actually have to do the fat $ body fat every single time if we specify the data here. Okay, so let's go through. We've got density. We're going to do that plus, so this is building our model equation where we're just saying each of these are additive to our model. Height, can't spell, plus adiposity, plus neck, plus chest, plus abdomen, plus hip, plus thigh, plus knee, plus ankle, plus biceps, plus forearm, plus wrist. All right, let's look at this and double check that we haven't forgotten any. Indo, if you look at the data set, is actually just a variable that says what is the individual. So this is sort of like an ID for the 252 individuals that were surveyed. So this wouldn't be a variable that we would want to include in our model. So this is our response variable, body fat. And then we have density, age, weight, height, adiposity, neck, chest, abdomen, hip, thigh, knee, ankle, biceps, forearm, and wrist. All right, let us run that. So we didn't get any errors, so that's good. That means we didn't misspell anything. And again, we get this list over here. So what we're going to do is what we did before, where we did summary of fit. Okay. And we'll get this much more detailed model table than what we got before. So first it's going to tell us what our formula was. This is what we put in. And then it's going to give us this more complicated model table where it lists out all of the different variables that we had. And then it's going to give us some p-value over here of which ones are statistically significant in predicting our body fat. And what you'll notice is that it's rank ordered. So the highest p-value is down here, wrist, and the smallest p-value is up at the top, and that's going to be density. And in fact, density is the only significant variable for this. And we can actually do a core test, like we did before in the previous video, between body fat and density. And, saying formula is missing. Okay. I think if I did it the other way. See, it doesn't seem to like the tilde symbol here. We get the same p-value, and then we get this very, very tight correlation. But you'll notice that this is a negative correlation. So density is inversely proportional to body fat in this data set. We're going to pick this data set back up when we go in a graphic analysis of data, where we're going to plot density and body fat together. This video is focused more on looking at the statistical relationships between these rather than exploring them graphically. All right, that concludes this video, and the main concepts that we talked about in this video, as just a quick summary, were practicing reading in data sets with more complexity, looking at things like NA strings and specifying those, and strings as factors. We made box plots with factor data. We subsetted our data in a couple of different ways, and then we fitted our data to two different statistical model and analysis of variance and generalized linear models.